Okay, I'm so sorry about the delay, everybody. Um, I suppose we should probably just get started. Hi, welcome to the Testing the Water webinar. I'm Coda. I'm an AmeriCorps member. I'm with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement, which we accomplished through locally led education efforts and community engagement projects to address local conservation concerns. Before I hand it over to Dan, just a bit of housekeeping. Your cameras are going to stay off. You're going to be muted throughout the presentation. Please type any questions that you have in the chat or the Q&A section, and we'll answer those either during or after the presentation, depending on what Dan wants to do. This presentation will be recorded. We'll upload it to YouTube within a couple of weeks or so. So if you missed the presentation, if you want to go back to something, or if you want to share it with anybody, you'll find it there fairly soon. Uh, After the presentation, we're going to have a quick survey. It should take less than a minute to complete. It helps us support the Conservation Nebraska program. So we really appreciate you taking the time to fill those out. If you want to talk to Conservation Nebraska regarding conservation issues in Nebraska, or to find out more about what we do, I will put our email in the chat in just a sec. Tonight we welcome Dan Snow from it's the UNL Extension office, am I right?
Nope, the Nebraska Water Center.
Oh, you're from the Nebraska Water right. I'm so sorry. Uh Today we welcome Dan Snow, Dr. Dan Snow from the Nebraska Water Center, and he's going to talk to us about water quality in agricultural landscapes. All right, go ahead.
First, are the slides in presenter mode from your side?
Yeah, I can see them.
Okay, you don't see you just see the slide, not the other icons.
Sorry, what?
Well, like the presenter, it's not in presenter mode, is what I'm asking.
Um, yeah, no, we can only see the slides.
Okay, great. All right, well, thanks everyone, and I appreciate the chance to talk a little bit about water quality. As Coda mentioned, I'm Daniel Snow, Director of the Water Sciences Laboratory, part of the Nebraska Water Center and Dougherty Water for Food Global Institute. I'm also a professor in the School of Natural Resources. I've been working in Nebraska pretty much my whole career. I've uh, learned a lot about water quality, particularly groundwater quality, and that's what I'm going to talk about in this presentation and hopefully come up with some solutions for addressing water quality issues in agriculturally intensive landscapes. So what is intensive agriculture? Intensive ag is characterized by high levels of inputs and outputs per unit area. You might recognize this air photo. It's actually a satellite image of circular crop fields in Haskell County, Kansas, showing all those center pivots. That's something that the Great Plains has become iconic for as a flyover area. When people look out of the airplane windows, they can see all these green circles that appear in late spring and through early summer and into fall. We're using a lot of water. We're using a lot of fertilizer to grow crops in the Great Plains, and there are some consequences for that. Intensive agriculture, as we have it here in the US, uses more water, energy, and chemicals to maximize production. We can produce some undesired environmental consequences, and I'm just going to touch on some of those consequences in this presentation. Well, globally, the U.S. is not alone in increasing our water use, increasing water demand. This just gives us an idea of the world population, which everyone believes is going to get to about 9 billion people by the end of the century. At the same time, our planet is only has a fixed amount of fresh water. This graph from Peter Glick's publication on water resources shows a comparison of that population growth in comparison to the amount of fresh water that we have per unit of per person. And we've already approached or probably gone below somewhat about a cubic kilometer per person on this planet. And we're rapidly basically approaching the limit of our freshwater resources. 10 things everybody should know about water. This is from the Smart Water magazine. The Earth has about 525 525 million cubic kilometers, and 2% of that is frozen. 97% is found in the oceans, and 80% of that is inland waters or surface. Only about 2.5% of the water on Earth is fresh water, and that is really practically the water that we have available to us in society for drinking water, for irrigation, often for industrial uses. And a lot of that fresh water is actually on the surface. We can't access it very easily. We have about 20% is underground or in the atmosphere, and so really only a small fraction of the available fresh water that we have on the planet it occurs as groundwater. Groundwater accounts for about 97% of our freshwater resources, and it is used for about a third of the world's drinking water. It is used quite extensively for irrigation throughout the world, and about 25% of that groundwater is used for industrial purposes. So what's happening along with demand of water? We're also increasing our use of energy. If you may have heard about this water energy nexus, this really kind of gets to the crux of the matter, is that we're ramping up our energy use for um, using fresh water like groundwater. This graph shows the change in population compared to water use and projected water use, in particular groundwater use. That dark black line at the bottom is a groundwater use up through 2020, projected up through 2050. We really are getting to the limit of the amount of and our capacity for using fresh groundwater for crop production and actually all uses. It's kind of interesting to note on this graph that the effects of COVID pandemic are actually seen in this, just some blips in the amount of energy that we used and the amount of groundwater that we were using was slowed somewhat during the COVID pandemic. So I found that to be quite interesting and really shows the extent of how the COVID pandemic had on us as a society. So just to recap, we have increasing demand for groundwater. Worldwide groundwater demand has increased by about 23% since the 1950s and will continue to increase. Groundwater depletion, where demand exceeds recharge, is becoming more common. You may hear about water scarcity. And the quality of the remaining groundwater, fresh groundwater, is becoming greatly diminished as a result, mainly of our agricultural uses for this fresh groundwater. Well, this gives us an indication of the High Plains Ogallala aquifer system that exists in Nebraska and to some extent in Kansas, Oklahoma, and Texas. There's a little bit in eastern Wyoming. And the colors refer to the thickness, that freshwater thickness that's available for our use. And you can see right away that that bulge, that blue dome that occurs in the sandhills is why Nebraska has gotten to become known as kind of the groundwater state. You know, we have the greatest share of that High Plains aquifer system than any place else in the U.S. And because of that, we were actually at a pretty good advantage, especially if we continue to want to use fresh groundwater for crop production. It really gives us an edge in comparison to the states south of us. If you look at the change in water levels of the High Plains Aquifer system, we can see that places in Kansas, Oklahoma, and Texas have seen very significant declines to the point where they can't pump water to the surface anymore. So this is, it really is a predicament. Kansas is just now grappling with the fact that they're going to have to stop irrigating many of the areas of cropland in the western part of the state. They never had very much water in the eastern part of Kansas, so they really are not affected as much as farmers and producers in the western part of the state. And of course, Texas and Oklahoma, they're also faced with almost no water. The wells are running dry in that part of the High Plains Ogallala system. So I want to point out that the risk for nitrate contamination, which is one of the most common contaminants in our groundwater, is actually highly correlated to these areas where they've seen significant declines or changes in groundwater levels. This shows risk of nitrate in contamination is pretty severe in Texas and also in those areas of Kansas. And even though Nebraska has a lot of fresh groundwater in comparison to those states, we have a lot of places in the state where we have a high risk for nitrate contamination. And that's going to be a big part of my talk this evening. So one of the messages I want to get across in this talk is that, at the same time as we're using this fresh groundwater, we're also changing the composition, the chemical composition. And this is some data that was published in a U.S. Geological Survey report that shows the trends in dissolved solids content or the salt content of many parts of the High Plains Ogallala system and nitrate. And we can see that everything is going up. So we're making our groundwater saltier and we're increasing the nitrate concentration over time. And this is data that goes back almost let's see, 1930. I'm reading that right. Yep. Early between 1930 and 1940. So we have some data. This is actually data that was acquired by the U.S. Geological Survey, and it clearly shows that we're changing the chemical composition of this fresh groundwater. Well, if you look at a cross section of many of the areas in the High Plains Ogallala Aquifer system, including Nebraska, it really is not too surprising that we're changing the chemical composition. The more we pump of that fresh groundwater to the surface, the greater consequences for salinization. When that water gets pumped to the surface, we get that water is evaporated, subject to evaporation and transpiration, and that effectively increases the dissolved solids content. And in addition to that, any salt, like fertilizer, is just a salt that we add to the surface, will be carried back down to the water table. And you basically are just recycling this irrigation water in many of those areas where we're pumping it to the surface. At the same time as nitrate contamination, we're also starting to notice trends in geogenic contaminants like uranium and arsenic. I did my PhD work back in the early 1990s on uranium contamination in surface and groundwater in Nebraska. And then a few years later, my colleague Carrie Weber and one of her PhD students showed that there was a good correlation between nitrate contamination and uranium concentrations in these aquifers, including the High Plains Ogallala system. There is not a direct one-to-one correlation. It's more of a spatial correlation. So in places where we see high nitrate, we have a high probability that we're going to see high nitrate. And then something that we hadn't really noticed until recently is that we're also starting to see some changes in the arsenic concentrations. So arsenic is another geogenic contaminant. It's naturally occurring in the soils and sediments. And we think that changes in the chemistry of the groundwater is actually causing this arsenic to become mobilized and the concentrations to increase in this fresh groundwater. So it wasn't too long ago that this was published in a paper from The Lancet. planetary health, and indicated that uranium is an underappreciated contaminant in U.S. Public drinking water system. This shows a map of areas where they're seeing elevated concentrations of uranium. In particular, we have quite a few counties in Nebraska that are dealing with high uranium concentrations in their public water systems. This paper was just published not too long ago, 2023. One of my colleagues, Dr. Aruna Malakar, and I did a bunch of work in the Hastings Wellhead Protection Area, Hastings, Nebraska. We looked at groundwater chemistry in the Vado zone, or the unsaturated zone, and we came up with a story that we think explains why we're seeing increasing uranium and arsenic in comparison to high nitrate in some of the aquifers in central Nebraska. So it's all related, and I think that the point of this is to show that high nitrate, high uranium, high arsenic, it's all it's starting to make sense hydrologically and geochemically. So along with those naturally occurring contaminants, arsenic and uranium and the fertilizer nitrate, we're starting to see more traces of pesticide residues in U.S. groundwater. This was published in 2020, it looks like, and they had done a survey. This is also a group from the U.S. Geological Survey, where they collected a whole bunch of data from aquifers that were supplying public water systems. And this shows the distribution of pesticides, best pesticide concentrations in areas with a triangle or a circle with a red ring around it. Shows that those concentrations are getting up to levels that we should start to be concerned. We don't have as much data as we do for uranium and arsenic, but we have quite a bit of data now that shows that areas with intensive agriculture tend to be areas where we're going to see increasing concentrations of pesticide residues. So what are the consequences of contaminated groundwater? Well, there's going to be continued monitoring that we have to do to establish what kind of levels are in our groundwater. And when they reach certain concentrations that are potentially hazardous to human health, we're going to have to pay to treat that water before it's used for drinking. There's going to be increasing disposal costs for waste products that are produced during treatment of drinking water. There's probably going to be some human health costs. Really, most of those are unknown at present. And it really it's going to impact our standard of living, especially in rural areas like Nebraska. We have a reduced value of this fresh groundwater resource. If you think about it, maybe 100 years ago, our groundwater was virtually uncontaminated, and now we've really changed the value of that water beneath the surface just because we're adding contaminants to it over time. So this shows kind of the situation now. The probability for public water systems in the U.S. For exceeding the maximum contaminant level for nitrate and the observed groundwater nitrate violations in between 2013 and 2017. All those red dots, you can see that it isn't just Nebraska where that's happening, but this is just public water systems across the U.S. And we have some areas where we have a lot of clusters, probably don't have as many public water systems in the High Plains Ogallala area as maybe out east or in Wisconsin and Minnesota. But we have quite a few in comparison to the population served in other areas. All right. So maybe some of you have seen this. This was published by the Department of Environment and Energy, recently renamed Department of Water, Environment and Energy, looking at data. This is again data that's been stored over time in the Nebraska Agrochemical Clearinghouse database online. And then they attempted to model or predict which areas are going to be most likely to have high groundwater nitrate concentrations. Really, everything that's above 3 is not natural. It's got to be influenced by some anthropogenic source like a fertilizer or other nitrogen source. If concentrations are getting between 5 and 10, those are probably areas where we have intensive agriculture that's contributing nitrate from the surface. And if it's above 10, well, we really need to treat that water to make it safe for human consumption. And this is kind of the state that we're in now in Nebraska, as we have quite a few areas in the state where we have to start treating, if we haven't already, nitrate levels before we can drink it. Well, using that same clearinghouse data, we did some statistical analysis of for Nebraska and looked at what are the risk factors for high groundwater nitrate. And basically, it boils down to we have very sandy soils, we have high irrigation pumping at the surface, high irrigation well density. In many places, especially along the Platte River and the Elkhorn River, we have a very short distance to the water table, and we have a thin vadose that interface between the surface and the water table. So, taken together, all those things correlate with areas where we see high groundwater nitrate. You notice it's not evenly distributed, it tends to be along the Platte River and Elkhorn River watersheds. As those tend to be the areas where we have the greatest intensity of agricultural production. All right, so what can we do? One thing we can do, and we found this from one of the research projects that I was involved with in the early 1990s, is we can use less water. This is from our management systems evaluation area located near Shelton, Nebraska, out in the Central Platte Natural Resources District. And what we found over about 6 years of monitoring in comparison to, or when we were comparing center pivot, where we use about half as much water as we would for surge or conventional irrigation. If we use less water with a sprinkler in comparison to a furrow, we're more likely to, or we're less likely to leach nitrate from the surface into the local groundwater. So this is one of the first studies where we demonstrated that just using less water, using more water conservation practices in the field helped maintain or even potentially improve groundwater quality. And then there were many studies since then that support this assertion that if you use less water, you're less likely to leach nitrate from the surface below your irrigated cropland. And we also found that using less water reduces pesticide leaching. In that same study, we measured groundwater concentrations of commonly used herbicides, and we found that overall, the concentrations of commonly the herbicides that were used at the surface were greatly reduced when we used less water through pivot irrigation in comparison to furrow or gravity irrigation. So those are two really simple practices, and those are practices that have been changing anyway because pivot irrigation uses less labor in delivering water to crops. That was going to happen anyway, and it's a good thing that it also helps preserve and reduce contamination of local groundwater. And this shows that this is the same sort of trend that we have in the U.S. U.S. harvested irrigated acres for selected crops in the United States, while we're increasing the area that we irrigate for corn and other crops, we are reducing our use of gravity, and we're converting many more fields into pressurized or pivot sprinkler type irrigation systems. So that's actually a good thing overall for the U.S., that we're changing practices that allow us to use less water at the surface for crop production. It's not only going to conserve that fresh water, but it's going to reduce the impact of intensive agriculture at the surface. So what are some other things that we can do? Well, number one is reduce water use. We can reduce nitrogen fertilizer rates, and that's something that has been the focus of many of our agronomic colleagues. Is they're trying to come up with ways that we can reduce fertilizer use and at the same time not affect crop yield, because crop yield is the most important parameter for most producers, is they just have to make money when they're growing crops. We found that applying fertilizer during the growing season is a good thing. So that's when the plants most need it. So fertigation has become a more common practice that will probably reduce the impact to local groundwater. We can plant non-legume cover crops between growing seasons to help hold that nitrogen in the soil. That tends to be more of a practice that we would use in areas that are less dry and have less sandy soils than the really sandy soils in the Central Platte and in the Elkhorn watersheds. And then that last practice is the use of controlled release fertilizers. If we apply a fertilizer, say as an extended release or a controlled release fertilizer, something that might be encapsulated, that also tends to reduce the amount of nitrate that's lost either through surface runoff or leaching. So why do we care about high nitrate? Why do we have maximum contaminant levels? Many of you are probably already familiar with this. Methemoglobinemia or blue baby syndrome was identified probably back in the 50s as a consequence of high nitrate in drinking water. Um, there's we found in the decades since then there's a possible association between chronic high elevated nitrate exposure during pregnancy and human malformations or birth defects. I know Dr. Martha Rhodes is something that she's working on quite a bit to look at the association between nitrate in drinking water as well as some pesticides and birth defects. And then my biggest concern is it's not just nitrate. We're seeing traces of these geogenic contaminants like uranium and arsenic, as well as some pesticides and pesticide degradation products. If you mix all those together, then we're more likely to have maybe some synergistic human health effects that we don't really understand and really haven't bothered to study very well. So who is most affected by contaminated fresh groundwater? Well, we've been looking at this for several decades now. There was a study published in the late 1990s by the U.S. Bureau of Reclamation that indicated in Nebraska we had 35 to 40% of our public water systems were affected by high nitrate already in the 1990s. That 2024 study by the Department of Environment and Energy identified over 170 public water systems that were addressing high nitrate with 9 on administrative order. What that means is that they have not been able to deal with the problem. And it's estimated that about 20% of Nebraskans use private domestic wells for drinking. Those are totally unregulated, and we don't really know the extent of nitrate, high nitrate in those wells. There's roughly 145 to maybe 145 to 150,000 unregistered or registered, domestic wells in Nebraska, and maybe a quarter of those are registered and probably have had some sort of testing. These are not regulated under the Safe Drinking Water Act, and there's no requirements. All testing of domestic wells is voluntary, and we don't really know what the health impacts of those. In comparison to public water systems, we have the Safe Drinking Water Act, and any public water system is required to do at least annual testing and demonstrate that they are able to produce and supply ground or drinking water that's deemed safe by the U.S. EPA. Public wells that are used for drinking are not subject to that requirement. For public water systems, the treatment costs keep going up. This is a study where we looked at the 20-year treatment cost for Northeast Nebraska and then an area from Central Nebraska. Mean 20-year cost for treating high nitrate was between 400,000 and 3.5 million for a rural population of about 18,000 people. Adjacent to that shows an image of the Creighton, Nebraska water tower with a population a little over 1,000. They installed a reverse osmosis system in the early 1990s, and then about 10 years ago, they had to invest in an expansion. It cost them 1.2 million, and then ongoing maintenance costs about 360,000 per year. Plus, they're projecting future equipment costs just to keep their drinking water system in compliance with the Safe Drinking Water Act is between $3 and $4 million. So that gets to be pretty substantial for these smaller communities across Nebraska and really across all the Great Plains when they have the concentrations continue to go up and our rural populations are in decline. So who's going to pay those costs? Well, that trend is increasing across the U.S. This shows a comparison between capital equipment costs, what we're investing in treatment systems, and then the operation and maintenance costs have just been increasing since the 1980s and will continue to go up as contaminants are finding their ways into the wells that are used by U.S. public water systems. And then, part of this treatment or infrastructure cost is really being put off. We've leveled out or flattened our treatment equipment investment, and we're not keeping up really with the demands of these public systems. So something's going to give. Basically, we're not investing enough in safe drinking water in the U.S. And at some point, we're just going to have to make a decision that it's something that we have to do. So the rest of my talk is going to be about the vulnerability of private or domestic wells. This image shows the kind of the situation as a comparison between a domestic well on the right-hand side and public water supply system. Public water wells tend to be a lot deeper. They tend to be constructed much more effectively to reduce contamination from the surface. They have a well screen that's situated much farther below the surface than a domestic well. And so almost always domestic wells are going to be more susceptible to contamination from the surface. As I mentioned earlier, they're not regulated under the Safe Drinking Water Act, and therefore we really need some better ways to reach out and look at the quality of drinking water used from private or domestic wells. Well, one program that I've been involved with the past 8 years or so has to do with outreach and education. And I think this is a pretty cool program. I'm really excited about it. I'd like to see it continue and expand. It really provides a way to communicate differently about water quality issues in our communities, or rural communities in particular, and involve lots of stakeholders in the decision-making process about what we can do to minimize the impact of intensive agriculture in those communities. It gives us a way to engage water users, the students and teachers and residents in a community in the data collection process, and then they can make some informed decisions from the data that's collected. It provides us with an innovative communication and data collection method. Really, some people call this citizen science, but I'd like to call it youth-led participatory science. And it gives us a window into a domestic well water quality that we wouldn't get through any other way. The Know Your Well program is basically summarized in this slide. High school students across Nebraska have participated in this. They receive a brief lecture on hydrology and groundwater in general and an explanation about the program. They're guided through a field demonstration on proper well sampling and use of test kits. We work really hard to try to address data quality concerns because these students and even their teachers are not professional scientists. They're all volunteers. So we've worked really hard in this program to make sure that we get consistent and accurate measurements as well as locations of these wells. The students are trained how to collect and preserve samples that are sent to the Water Sciences Laboratory for independent comprehensive testing. And then they use test kits and can compare their test kit results to what we get in the laboratory. Well owners who participate in the Know Your Well program are provided with a copy of the laboratory test results, not the student test results. And then along with those test results, they get information on a comparison to Safe Drinking Water Act levels and then information on how they might treat their well water if necessary. Well, the programs was established through a grant from the Nebraska Environmental Trust in 2017. Um, it established the framework and kind of the program. Subsequent grants, 2022 to 2025 from the Nebraska Department of Environment and Energy, allowed us to improve our web app and grew the network to almost 40 schools who have now tested probably over 450 domestic wells across Nebraska. We're just finishing up an EPA Region 7 environmental education grant that allowed us to develop a very comprehensive curriculum that the teachers can use that makes it a lot easier for teachers to implement and adopt this as part of their classroom activities. So here's the current workflow. Know Your Well regional leaders who we have identified. Typically they're with a natural resources district, although we have some regional leaders that are located at some of our four-year colleges and county health departments. Those regional leaders connect teachers with a program, and then they're the ones that are providing training on well construction and groundwater contamination. They help students locate registered wells using the Nebraska Department of Natural Resources well registration database. And then those regional leaders supervise well sampling and testing using the commercial probes and test kits that the students get to use. And then everyone is trained in the use of this Know Your Well app, which is available on the website. The app is pretty cool. It's free. You can download it to your phone or your computer and allows you to input data very easily as part of the program. The login for the Know Your Well app uses a Nebraska Educational Service Unit's infrastructure. That is, it really is tied directly to the schools and school districts. You have to have an email address on the Nebraska ESU to access the Know Your Well database and be able to use the Know Your Well app. You can access the app from our resources page, knowyourwell.unl.edu. If you're already in a school and you have a school email address, you can select your school district and log in using your school credentials. And then what this does is it provides a secure way for students and their teachers to collect and upload data automatically to a central database. They have access to this data as we do here at the university, but otherwise the information is kept very secure so that well owners' identities are kept anonymous. So this is a list that's available on the website. We have lesson plans for the Know Your Well program schools. We have the data collection app that I talked about, and then we have lots and lots of tutorials on how to use the test kits, the sampling probes, test probes that they use in the field, how to access the well registration database, um, and then how they get information from the Natural Resources District's well interactive map on the DNR website, as well as we provide well owner consent forms and instructions, detailed instructions on how to collect and preserve those samples. This is really a very unique feature in comparison to other citizen science programs or even Test Your Well Night that might be run by a natural resources district, is we have a very comprehensive screen. It's not just nitrate that we're testing for. And the students are all ones that go out and collect the samples and make the measurements. So they get really involved in the data collection process. They'll measure pH, temperature, conductivity at the wellhead. Conductivity is just a measure of the dissolved solids content. They have a call alert test kit where they can actually determine if the well has coliform and E. coli bacteria present in a sample from that well. Of course, they can measure nitrate with a portable test kit, and they can also measure some metals like iron, copper, and manganese. We started out the program with an atrazine test strip. That strip's no longer available, so we've expanded our or test kits into other parameters such as ammonia and one or two other metals. The split samples is another unique aspect of the Know Your Well in comparison to other citizen science programs, is that we're getting these samples once properly collected and preserved, tested in a laboratory. The Water Sciences Laboratory uses a pretty extensive quality control program, so we provide really good, accurate data to the well owners. And then the students and teachers can access the data that's stored in their website. Our website it's a secure online database where the owner identity is kept confidential. So this just shows some comparability between the test kit results and the laboratory results. Each color is the same school, the range in, say, nitrate concentrations in comparison to the laboratory test results. And you can see there's pretty good agreement, especially for some schools, between the test kit result and the laboratory result. So I would say that this actually gives us a good justification for using these test kits as a screening tool. If you have high nitrate in a test kit result, you're probably going to have high nitrate in the laboratory test result. We were pretty lucky. We got all the data from that first grant, and we collected it, and we got a paper published in Environmental Sciences and Technology Water, evaluating youth-led citizen science for improved monitoring of domestic well water quality. We found in the first phase of this program about, I think there was close to 300, no, 250 wells that were sampled. We had areas that definitely had high nitrate, higher than the maximum contaminant level. We didn't have any high atrazine in comparison to the maximum contaminant level, which is a good thing, but we were seeing a pretty frequent occurrence of one of the metabolites of atrazine, known as diethylatrazine or DEA. And then the other things that we found are arsenic, manganese, and uranium. As I mentioned, I did my PhD research in uranium, and we have quite a few wells that have uranium and arsenic at concentrations that are above the USA EPA guidelines for drinking water. Well, it's not just testing the water, it's also talking in the communities about local well water quality. And this shows an image from a group of FFA students from a school where they're given a presentation on the results that they were able to produce from their well sampling. We've had groups present at Junior Academy of Sciences meetings and conferences, as well as local natural resources districts board meetings. Public presentations by these students are heard by a broad range of stakeholders. One recent one was at the Central Platte Natural Resources District, where he talked about high nitrate and high uranium concentrations in their district boundaries. And it was a student that gave this presentation, which I thought was really cool. A high school student. He took this on as a student project in high school, wrote up the data, and gave a presentation on this trend that he found in wells that were just within his school district. So I thought that was really cool. So this is just my summary slide. This is the end here. I'm going to talk, I've given you a pretty good summary, I think, of how groundwater quality has changed under intensive agriculture and kind of fresh, safe groundwater is an increasingly undervalued resource because intensive agriculture that we've experienced over the past several decades, we've probably impacted the quality of that groundwater, and we need to value it more so we can put more emphasis on conservation practices that allow us to reduce the impact of agriculture. Agriculture is the single largest use and greatest threat to safe and sustainable use of fresh groundwater, not just in Nebraska, not just in the US, but everywhere. And it requires a responsible use of this fresh groundwater, requires better management through improved land management, improved water use through irrigation, better irrigation technologies and fertilizer application methods, as well as the basic science of understanding hydrology, hydrogeology, and water chemistry. So all these things are, in my view, are opportunities. We know what we need to do. We know ways that we can get our students, not just university students, but our high school students involved in the process. And I'd like to think that we can solve this problem eventually, as we can come up with ways that are going to protect this increasingly valuable resource in Nebraska and pretty much everywhere. So with that, I'll be happy to take any questions.
Before that happens, sorry. Um, I'm just going to send out the survey real quick. If you could complete that, that would be fantastic. We would love it if you would do that. Answer honestly, of course, and yeah, thanks. It
Okay,
looks like somebody's raising their hand. If you could put the question in the chat, please, that would be great.
looks like the first question we have is, are farmers required by law to report nitrate levels from the wells on their property? Which I know you kind of talked about this already.
Are farmers required to report groundwater nitrate levels on their property? Um, I think it depends on where their farm is located. I think some natural resources districts are requiring the farmer to sample and test, say, their irrigation wells. They're in general, they're not required to sample and test domestic wells. But if the Natural Resources District has introduced a phased management practice, phased means that they're trying to control or better manage land use practices at the surface. They may have a farmer sample their irrigation well and account for the amount of nitrate that's in that well when they're determining the amount of fertilizer that they're going to apply for that particular crop. I think that's that happens now. I don't think there's any requirement now to have them test private wells.
And then a follow-up to that specific question, what happens when the farmer's wells test high for nitrates?
Yeah, that gets back to the groundwater management areas. I know, like for example, the Central Platte Natural Resources District has a pretty detailed plan for addressing high nitrate in their district boundaries, and it's based on the groundwater nitrate levels. Say if it's below 5 milligrams per liter, maybe 3 milligrams per liter, they don't do anything. But if it gets between, say, 3 and 5 or 7 milligrams per liter, then they start working on educational programs. If it gets above that 10 milligram per liter, then they're going to institute some either some incentives or cost shares to use some of those conservation practices that I mentioned earlier, where they're using maybe slow release fertilizer or using cover crops to help reduce the amount of nitrate that leaches. They have to report the amount of fertilizer that they're applying and the amount of water that they're using. So the higher the nitrate, the groundwater nitrate is in their local groundwater, the more they have to adopt practices that will reduce nitrate leaching.
Perfect, thank you. Um, and then I guess this is kind of maybe before they're testing the water, but just in general, is there any work being done with farmers to reduce water use?
Yeah, again, that depends on the natural resources districts. So some districts are working really hard to control the amount of water because even though Nebraska has a lot of pretty abundant supply of fresh groundwater, there's places where they pumped it so much that the water levels are declining. So those areas in particular are reducing water use. They haven't even gotten to the point where they're starting to buy out cropland and so that they can just have non-irrigated land in their district boundaries, just because they don't have enough. So that's kind of an extreme example. There are subsidies, say for purchasing a pivot, if you want to convert a furrow or gravity irrigated field into a sprinkler irrigated field, they'll maybe provide a cost share to purchase a center pivot system or maybe some nozzles that reduce water use. Most NRDs, especially if they're in an area that is affected by high nitrate or declining groundwater levels, will have some sort of a cost sharing program where they try to help the producer to conserve what they have and reduce nitrate concentrations.
And then the next question, it's talking about like large corporations using massive amounts of water for evaporative cooling. Do you happen to know like an estimate on how much they use and then what is being done to regulate their water use? I know that's not ag focused.
Hmm. Yeah, again, this goes through the Natural Resources District and the Department of Natural Resources. Department of Natural Resources has a process where industry, actually anyone that wants to install a well, they have to apply for a permit, and that permit has to state how much water they're going to be pumping. And they have the right through that permitting system to either to grant that permit or to reject it, maybe not allow that well to be installed. So that's one way to control water use is through the permitting system. Another one is that say somebody's well in the vicinity of one of these industrial wells is impacted by uh, pumping. The water levels in their domestic well is declining. They can work through the NRD to to reduce pumping in that industrial well. The NRD has the authority to control the amount of water that's pumped. Industrial use is probably one of the lowest priorities in the state under their legal system. Municipal and domestic uses tend to be close to the highest in terms of priority. So drinking water is a higher priority, say, than in industrial use or irrigation.
Okay, thank you. So one question is, do you have best practices for those building new homes in rural Nebraska with a private well? And then wanting some recommendations for water purification systems, etc., and like
Mm.
test kits for the water for individuals.
Yeah, so the state of Nebraska State Health and Human Services Department laboratory has a new well owner. So if you install a new well and you want to have it tested for everything, they have a price for a new well quality kit. It's kind of expensive because it tests for almost everything that could be impacting water quality. For just somebody that already has a private well, I always say when they call me to have it tested for nitrate and coliform bacteria, E. coli. That's a good screen. And then if they're in certain parts of the state that are susceptible to uranium or arsenic contamination, I would advise testing for those things. And then as far as treatment goes, it really depends on the contaminant. Nitrate can be removed or reduced through reverse osmosis. That tends to be the least expensive option for treating high nitrate water, but it also produces a lot of wastewater. So you might have to consider that all that water that's used in treating your drinking water could be going into your septic system and then eventually contaminating the local groundwater. I'm not a big fan of reverse osmosis. If you can do other systems other types of treatment, maybe point of use treatment that is only for um, drinking water or cooking, you can use distillation or ion exchange is another way to remove contaminants. Again, it just depends on what's in the water. So the first thing you want to do is have it tested and then compare those contaminants to what is safe using EPA guidelines for drinking water.
Hey, just a reminder for everybody about the survey. I'm going to close it in probably about 5 minutes. I see a few people haven't responded yet. It would be really great if you did. Thank you so much.
Yeah, and then it looks like we have another question. This looks like I think it's the last one. How many times a year should you test for arsenic specifically, but I guess just other contaminants in general?
Mm. That's really a good question. I think a lot of people think, well, it's a one and done, but concentrations can change seasonally, even over the space of a few months. So of course, you can get carried away with testing too frequently. But I would say if you're in an area with that experiences high fluctuations in groundwater demand through irrigation, that you probably want to test it maybe in the spring and in the fall, maybe over the space of like a 6 month time window, and then maybe again the following year, and just see how consistent the contaminant concentrations are, because they can fluctuate by 50 or 100%, just because of these seasonal variations and contaminants, even like arsenic and uranium. So it's not something um, that we thought of, and we didn't really think that it would stay pretty static. But because we pump so much water out of the ground, we see some really significant changes in the concentrations over time.
All right, I think that was the last question.
Well,
Looks like we're coming.
if that was the last question, I'm gonna probably end it here, I think.
Yeah, we're coming up on
Um,
7.
this will be available on YouTube, in a couple weeks. Um, thank you so much for presenting, Dan. This was a very informative presentation. I'm sure I didn't know a lot of the stuff. Assume everybody here didn't, at least didn't know all of the stuff. It was really great to have you present. Uh, thank you so much. Thanks everybody for coming. And please check out our Facebook page or our Instagram or our YouTube page for more stuff like this. Uh, okay, bye.
Thank you. Have a good night.
Bye.